In this video, we're going to look at the concept of work from a physical perspective. So in physics, work has a very specific meaning. In science, work has a very specific meaning. And it's very closely related to energy. So scientists define energy as the ability to do work. So work must be pretty important if that's the only definition scientists can come up with for energy. Well, what is work? Work has to do with forces applied to objects and distances that the forces move the object. Okay, so those are the two things that make up work. So let's just think about it for a minute. If I take a box and I pull it, or let's say I push it with a force. And I move it this far. So the box ends up here. Well, the work done in that case is just going to equal the force times the distance that you move it, because they're both in the same direction. So the force and the distance that you move it, the displacement, are in the same direction. So what that really means is that all of your pushing force goes into moving the box. It's in the right direction to cause the box to move, right? Now I want you to think about a different scenario. If we were to think about maybe a little kid on a sled, right? So I'll put my little sled here and a little person sitting on it with a smile. And let's say instead of pushing like I did in the last example, I pushed forward and the kid would move forward. So let's not do it that way this time. Let's say that I pull the kid with the string this way. So my force is upward, because that's the way like I'm pulling the string, hauling him over to the mountain, right? And now I move, right? He moves a certain distance, so I'm pulling him and I'm walking while I'm pulling him and my force is up and he moves this distance d. Well, now I think you can picture that part of this force is causing the sled to lift up a little bit off the ground. And part of the force is causing him to move forward. And so it turns out that the work formula is not as simple as F times D. The general case of the work formula is how much of this force is acting in the direction of D. So if I was to consider the amount of the force, right, if I was to project that force down onto D, this is the force in the direction of D. So I make my little right triangle like I've been doing for lots of different units here. And so that we would call F, and I'll call it in the X direction. And because D is also in the X direction, I picked my X direction to be this way. And so the work done here would be equal to the piece of the force that's in the direction of the motion times how far he moved in that direction. So it looks like the same formula, but what is F sub x? Well, this little red vector is the overall force times the cosine of the angle. So it's the F times the cosine of the angle, and that gives you the component of the force in the direction of D. So the only part of the force that attributes to work, or that's included in the work, is the part that is in the direction of D. And then we multiply that F sub x vector by the displacement it moves in that direction. So the amount of work done is equal to F times the cosine of the angle between the force vector and the distance vector. and then multiplied by your distance vector or your displacement vector, because we're talking about a vector and displacement is the vector. Distance is different than displacement. Now, that, if we rearrange it, that formula can be rewritten like this: F times D times the cosine of the angle between them. But we know that formula. When I have a vector, if I said A times B times the cosine of the angle between them, we would have called that the dot product. And so work, because the work done on an object is equal to the product of the component of the work in the direction of the motion times the displacement you move in that direction, the work is equal to the dot product of the two vectors, the force and the displacement vector. And we can rewrite that as the magnitude of the force vector times the magnitude of the displacement vector times the cosine of the angle between them. And so the formula to calculate work is actually not too complicated because you've been practicing doing dot products. What happens, though, is the problems get worded in complicated ways. So let's do a couple, and we'll walk through a few of them. We'll start off with one that's fairly straightforward, and then we'll walk through different ways that the problems can get worded. So work, example number 1. A 50-pound force pulls an object 10 feet. The force is in the same direction as the motion. Okay, so we're going to take a little drawing. We're going to put a force of 50 pounds. And we're going to move this object 10 feet. So if we draw it out like that, these two are in the same direction. And so when I do this formula, I can either do F dot D, or I can do the magnitude of F times the magnitude of D times the cosine of the angle between them. And so clearly in this one, the angle between them is 0. So this would be cosine of 0, and we know cosine of 0 degrees is just 1. The magnitude is the amount of each thing, so this would be 50 pounds times 10 feet times 1, and we would get 500, and the unit is foot-pounds. That's the English unit for work. Now, what if I do, for example 2, the same problem, it's a 50-pound force, and the object moves 10 feet, but the force is at a 30-degree angle from the motion. How much work is done by the force? Well, if I take a very similar looking diagram, in now this case, I have my object. It's still going to move over 10 feet, but now I'm pulling it at a 30-degree angle with that horizontal motion. And so here's my 50. I can either do work equals F dot D, and I can do it in component form, or I can use the magnitude form, right? So this is the magnitude form of the dot product. And so I can simply plug in again. I have a 50-pound force. It moves 10 feet. But this time there's an angle, the cosine of 30 degrees. And so when I do that calculation, we get 50 times 10 times the cosine of 30, and we get 433 of work. So same force amount, same 50-pound force, same distance is moved, but because in this case, not all of this force is causing it to move forward. Some of this force is lifting up on the box. And so the only part of the force that's causing it to move forward is the x component. And that x component is 50 times the cosine of 30. That's the x component of your force, or the component of the force in the direction of the motion. So the 50 cosine 30, that's the component of the force in the direction of the motion, and then it moves 10 feet in that direction, so your work is 433 foot-pounds. Now, let's take a look at the first one. I'm going to go back to the first one. Let's just do it as components, right? So if we were to look at these two vectors, the 50-pound and then the 10-foot. Now, they're different units, okay? So 50 pounds and 10 feet, those are two different units, so they don't have to scale because they're not 50 feet and 10 feet. It's pounds and feet. So you don't have to draw the 50-pound vector 5 times the length of the 10 feet because they're not the same measurement. But if I was to do those vectors in component form, the 50 pounds, if I choose this to be my x-axis, would be 50, 0. The distance, the displacement vector, I should say, is 10, 0. I keep saying distance because when you go in a straight line and you don't turn, distance and displacement mean the same thing, but the correct term is displacement because it's a vector. And so if I do F dot D using component form, I get 50 times 10 plus 0 times 0. And so I still get the same answer, 50 foot-pounds. So you can find the work done by a force, either doing it with the magnitudes, so magnitude of one vector, the force, times the magnitude of the displacement times the cosine of the angle, or you can get them both into their component form and multiply and get the dot product using the component form. Okay, so let's do another one. Example 3, we have a work vector, a force vector. We want to find the work. Work is not a vector. Work is a scalar because dot products are scalars, remember. So a force vector of 20, 20 moves an object from position 1, 1 to 7, 2. Find the work done. Now I'm going to just sketch this so that we understand a couple of the pieces here. And what happens is you have to make a decision when you're calculating the work. Do you want, it has to be the dot product, so the work is the dot product of the force and the displacement. So do you want to go to the magnitude and direction form? And if you're going to do that, you're going to need to know the magnitudes and you're going to need to know the angle between them. Or do you want to go to the component form where you're going to need to know the components of the two vectors? So in this case, we know the component of the force vector, so I'm thinking it might be best to do the component form, but let's take a look at the picture. So the force vector is 20, 20. That means that it's a 45-degree angle, so if I went 20 to the right and 20 up, my force vector would be in this direction. Now I could easily find the magnitude of this, right? And I know that it's a 45-degree because it's a 20 and 20 is my x and my y. But let's take a look at the position vector. We're going to move this object from 1, 1 to 7, 2. So the displacement vector is that. Okay, now it might help when we draw this out to draw the displacement vector first. So let me just do that on a separate grid here, because that force vector doesn't have to be from the origin. So if I take my 1, 1 to 7, 2, there's my displacement vector. And then I can put my force vector of 20, 20 from here. And so just rather than starting it at the origin, there's my force vector of 20, 20. And here's my d vector. But my d vector goes from 1, 1 to 7, 2. And so I can actually get the component form by doing the subtraction like we've done. 7 minus 1 is 6. 2 minus 1 is 1. So the components of the d vector are 6, 1. The components of the force vector are 20, 20. So I think plugging this into the component form of the dot product is easiest. So we would say that the work is equal to 20, 20 dot 6, 1. And we know when we do that, we multiply them and add. So we get 20 times 6 plus 20 times 1. Oops, I lost my 0 there. So we get 120 plus 20 is 140. Now I didn't give any units on these. If we said that it would be pounds for the force vector and this was in feet, again we would get foot-pounds. So it depends on what units are given in your problem. So a force vector of 20, 20, moving an object from 1, 1 to 7, 2, I can get the component form of that displacement vector, and then I can just dot it with the component form of my force vector to get the amount of work.